Good morning, ladies and gentlemen. My name is Artur Gańczan, and together with Maciej Niedźwiecki and Piotr Kaczmarek, I'm the author of an article describing identification of fast time-varying communication channels with pre-estimation and regularization. Let me start by defining the problem that we solve in our paper. We consider a non-stationary system that can be described by the following equation. Here, theta is a vector of unknown time-varying parameters. Phi is a regression vector made up of previous values of a known input signal. Y denotes a known output sequence, and E is a measurement noise. All of the above-mentioned variables are complex valued. A typical example of an application in which such a model can be used is underwater acoustic communication in a full duplex mode. In this application, transmitter and receiver are typically in close proximity and use the same bandwidth. This means that signal received from a far-end transmitter will be contaminated with the signal from a near-end transmitter, in our case represented by U. Of course, the signal from the near-end transmitter is prone to the multipath effect, which justifies the FIR description we use. And the time variability of the model is caused by the motion of natural reflectors, which in the case considered correspond to underwater objects, surface waves, etc. The goal is to recover the E signal, knowing Y and U. And this task can be accomplished by identification of model parameters. The figure depicts typical trajectories of a simulated underwater channel. Derivation of our method requires the assumption that inside some analysis window, parameter changes can be described as a linear combination of some known functions of time. Under this assumption, we express our original model using a higher order but stationary model. Of course, this description is only valid inside the analysis window. Then we use the weighted least squares technique to obtain some evaluation of coefficients alpha, which we use to get the estimates of original parameters for the central time instant in our analysis window. Then the window is shifted by one sampling interval to the next position, and the estimation is repeated. This pointwise procedure we call the local basis function method, LBF. This approach provides high quality estimates of model parameters, but since the number of estimated hyperparameters alpha can be quite high, it also requires higher computational costs and also longer analysis windows to guarantee good conditioning of the regression matrix. Both of these drawbacks can be overcome if we use a two-step technique approximating the behavior of the LBF approach. This method consists of two steps. First, we obtain pre-estimates that are unbiased regardless of the type and speed of parameter changes. However, unbiasedness comes at the cost of a high variance of pre-estimates. That is why they cannot be used as a final product. So, to solve this issue, we propose a second post-filtration step. Please note that in order to obtain pre-estimates, one should know the true covariance matrix of the regression vector. In next slides, we will see how to overcome this problem. But first, we can compare results yielded by the exact LBF method and the approximate method that we call the fast local basis function, FLBF method. Here, red lines show the true parameter trajectories, while the black lines are the estimated trajectories. As you can see, the FLBF approach can provide estimates of comparable quality at a substantially lower computational cost. So how exactly are the pre-estimates computed? It turns out that the whole expression for the pre-estimates can be approximated by the inverse filtering of the exponentially weighted least squares estimates of system parameters. In this particular case, because the input sequence is wide, instead of EWS estimates, we can use the computationally simpler least mean squares estimates of system parameter trajectories. The estimates obtained in such a way can be seen as a true parameter trajectories contaminated with white noise with a large variance. Therefore, we again assume that inside some analysis window, parameter trajectories can be described as a linear combination of known functions of time. And we again apply the weighted least squares procedure to find estimates of alpha. Weighted function W is chosen so that it puts greater emphasis on data closer to the center of the analysis window. This scheme is in fact equivalent to the Sawicki-Golay filtration, and it turns out that if the basis functions and the weighting sequence are the same as in the LBF method, then this FLBF approach can be used as an approximation of LBF. In this article, we propose a further improvement of the FLBF procedure by applying a carefully designed regularization. It is well known that regularization can improve mean squared estimation errors by improving the bias variance trade-off. Please note that in our setup, we are not interested in direct regularization of hyperparameters alpha. Instead, we apply the regularization to the vector of variables representing model parameters. The formulation of the problem is as follows, and it can be shown that the regularized estimates can be obtained quickly by a simple transformation of the FLBF estimates. Now, as we have this result, it is time to ask a question: how to choose the regularization matrix? To find a matrix that will improve the MSE score, we need few additional assumptions. Firstly, we assume that the input signal is a zero mean wide sense locally stationary, independent and identically distributed random sequence, which is actually not a very restrictive assumption in communication applications. Then we also assume that the noise is independent of the input signal and similarly zero mean and wide sequence. Finally, we also require parameter trajectories to be wide sense stationary processes independent of an input signal and with known correlation matrix. If the correlation matrix is not known, it can be pre-estimated using the results of preliminary experiments. Now, let us define the MSE matrix. And it can be shown that under the previously listed assumptions, a matrix of this form minimizes a mean squared error of the FRLBF estimates. One potential issue is with the variance of the pre-estimation noise, but this formula can be replaced by the suboptimal solution. And in a suboptimal solution, we can replace the pre-estimation noise variance with its estimate obtained using the FLBF estimates of system trajectories. The power profile of parameter trajectories might change in time due to the changes in the underwater environment. In such a case, we propose to simultaneously run several algorithms equipped with different regularization matrices, and at every time instant t, we choose the one that minimizes the sum of squared leave one out output interpolation errors. These errors require the use of leave one out cross-validation estimates of theta. We obtain such estimates by excluding the central observation from the estimation process. But that does not mean that we need to solve another least squares problem to find them. In fact, it turns out that they can be obtained using this formula involving the eigenvalues and eigenvectors of the regularization matrix, which can be pre-computed and stored in the computer memory. We also need here the pre-estimate and the FRLBF estimate, and that is all. The estimation scheme that we have already presented can be further improved if instead of LMS-based pre-estimates, we would use something called enhanced pre-estimates. To obtain them, we first compute LMS pre-estimates, and we continue with the FRLBF procedure, and finally we use FRLBF estimates to compute pre-estimates with a correction term. The advantage of the enhanced pre-estimates can be clearly visible when one analyzes estimation errors of the pre-estimates. The second part is the same because it is the contribution of measurement noise. The first part, however, depends on the difference between the estimates and true parameter trajectories. So, by improving the estimates that are a basis for pre-estimation, we reduce pre-estimation noise. This results in improvement of the final estimates. When we will take a look at plots showing pre-estimates, which are depicted with the black lines, the benefits of enhanced pre-estimates are clearly visible. All of the discussed algorithms were tested using computer simulations. First, we generated 50 parameter trajectories by low-pass filtration of random Gaussian signals and rescaling them so that the expected variance of parameter trajectories would decrease exponentially. This reflects the power absorption loss in a real channel, because the greater the reflection delay, the greater the energy loss. An example of a frozen impulse response of the simulated system is depicted here. As an input signal, we use the circular wide binary sequence. The measurement noise was circular wide Gaussian. And to measure the quality of our estimates, we use two measures, the SIGF measure in decibels and the time averaged fit measure. Both measures were averaged over 20 independent realizations of the amplitudes of parameter trajectories. During our simulations, we started with the comparison between the LBF and FLBF performance. Then we ran 3 regularized algorithms with different regularization matrices, reflecting our prior knowledge about the power profile of the estimated impulse response. Note, however, that none of the gamma constants is equal to the true constant from the previous slide, which was 0.69. As you can see from the table, the regularization can improve the results of the FLBF estimator, even if gamma is far from the true one. We also applied the adaptive procedure, which yields results close to the best ones. Results here are the effect of the application of the FRLBF procedure with the enhanced pre-estimates. As you can see, each of those results is better than the corresponding result for LMS-based pre-estimates. Here we can see the exemplary estimated impulse responses, which are depicted with red lines and superimposed on true impulse responses. As you can see, the main advantage of regularized methods is visible for parameters which take values that are close to 0. So, to summarize, The problem of identification of a non-stationary stochastic system was considered and solved using the time-localized variant of the regularized basis function approach. The FLBF and LBF algorithms yield estimates of comparable quality. The proposed regularization can substantially improve FLBF performance at very moderate computational costs, and the regularized matrix can be chosen in an adaptive fashion, and the proposed adaptive procedure yields results that are either better or comparable with the results provided by the best algorithm incorporated in the parallel estimation scheme. Thank you for your attention.